Hey guys, it is Miss Broussard. I know I'm not Miss Thompson, but I was getting ready for air pollution, our chapter 15, which is our newest topic, and I realized that there wasn't an Edpuzzle for this unit. Well, I mean, there was, but it was one of the Bozeman science videos, and I feel like it was a pretty good video, but I don't know. I just feel like he didn't explain some things very well. So I was like, I'm going to do the video today. So hope that's okay with you guys. I'm actually super pumped. I just ate a whole bunch of raw coffee beans. So I'm feeling really excited and energetic. But that's where I'm at. Anyways, excited to talk to you guys about air pollution. All right. So just kind of introducing the topic. Y'all have heard of air pollution before. We deal with it all the time. You guys know this stuff. But formal definition, we're talking about any airborne particulate matter, but we're also talking about particulate matter would be just like suspended matter, so such as like dust or smog, forming particles, ash, soot, things like that. But we're also talking about organic molecules, so nitrates, we're talking about sulfuric acid, we're talking even about carbon dioxide and ozone layers. So any sort of molecules that are causing some havoc in our atmosphere is considered an air pollutant. We've got a couple different sources for these, and we're going to get really familiar with them in this unit. We can have natural sources. So forest fires is going to release a lot of nitrogen molecules. You guys know this. We've gone over this a lot. Nitrogen is a key nutrient in building organic matter in plants. So forest fires can release those. If you think back to the sulfur cycle, we talked about how volcanoes release sulfur dioxide. That's one of the parts of the sulfur cycle. You can revisit that if you want. But we also have anthropogenic, anthro meaning human, so human-based sources as well. So automobile emissions, any sort of combustion reaction, smokestacks, even things like when we're mining for coal. These are all releasing air pollutants into our atmosphere. You guys also know from previous, I love apes because everything kind of ties in together, but air pollution doesn't stay local. So acid rain can travel, or all the like different effects can travel. So you guys, we've talked about global wind patterns and the Coriolis effect. So if I release some toxins, or if I release some pollutants into one part of the earth, it's not going to just stay there. Wind doesn't like just keep things in one spot. Wind and global wind currents are always moving things around. So we're traveling and transporting all these different pollutants around our atmosphere. All right. There's a couple major air pollutants. You and guys are actually going to do like a murder mystery, like who done it kind of thing to help you guys learn these different pollutants later this week. But we've got sulfur dioxide. This one's huge, released from combustion reactions. Sulfur dioxide is one of the major I guess, like villains that's in charge of acid rain and also gray smog, London gray smog. Nitrogen oxides, we say oxides because nitrogen oxide can actually take lots of forms. It can be NO, NO2, a whole bunch of different combinations of that. But those are formed usually from like electricity, like energy consumption. That's how those nitrogen oxides are released. And this is actually our huge guy who's in charge of photochemical smog, which we're going to talk about later in this video, so stay tuned. Carbon monoxide, you guys know this one. It's the one that's formed or released whenever we're using thermal heat energy. So if you've got a gas stove, that gas that is powering that stove is usually carbon monoxide, where it has it in it. That's why we've got that the scent added into the carbon monoxide, because it is extremely poisonous to us. Ozone, you probably are surprised to see on here. I remember I was really surprised when I learned about this. I was like, what? Ozone's really beneficial. Why is it a pollutant? Well, ozone is extremely important. We're going to talk about why it's really important later. Ozone is really important when it's way up high in the stratosphere. But if the ozone is closer to us down here in the troposphere, that's where it actually causes problems. It is kind of toxic to us. Lead used to be in a lot of paints. We used to have lead-based paints. And so as older buildings are starting to have their walls and paint chip, that's releasing some lead into the atmosphere. I want to talk real quick about VOCs, volatile organic compounds, because they're going to be really important when we talk about the formation of smog. VOC, so volatile essentially means that these are molecules that have a very low boiling point, okay? The boiling point is the temperature at which a liquid turns into a gas. So VOCs are molecules that tend to have a very, very low boiling point, which means that they boil at lower temperatures, which means that they're primarily airborne, or it's a lot easier for them to become airborne because they have these low boiling points. Anytime I think of a VOC, I think of something that has a scent. So perfumes, I think of, well, now I'm blanking on everything. All of our fragrant plants, so conifers, citrus fruits, you can smell the plants. Those scents are actually VOCs. Formaldehyde, which is a preserver, that has a lot of VOCs. So I always think of like smelly things whenever I think of VOCs. Okay, so I'm gonna pause the video here for you guys to take a question, but you guys are gonna hopefully become very familiar with this chart. It's kind of goes over everything. It's getting cut off a little bit, but one last one I was gonna pay attention to is carbon dioxide. It's a very recent addition to the list of major air pollutants. And you probably don't think like, oh, carbon dioxide, like, you know, that's a natural thing, that's not an air pollutant. It is natural, you know, it's produced from that respiration. It's really critical for plant growth, for them to go through photosynthesis, but carbon dioxide, due to its detrimental effects that we're seeing more and more of in terms of climate change and its role in altering our planet's chemistry and our planet's atmosphere, it is newly considered an air pollutant because it's now occurring in way higher, way greater quantities than we've ever seen before. I feel like I'm talking really fast. I apologize. Okay, now I see what I feel like I'm moving my head all over the place. Okay, I had too many coffee beans. So particulate matter, again, these are kind of like anything that is airborne matter. So I always think of dust, soot, ash, even like, I don't know if any of you guys do woodworking, but if you're ever sanding, a lot of people when they're sanding will wear a mask because as you're sanding, the wood turns into these really, really, really fine, I don't know, wood dust. I'm sure there's a better word for that. But even that, anything that's super, super tiny in size that's suspended can actually cause problems because it's like our nose. Yeah, our nose is really good about catching particles that are bigger than 100 micrometers. Which is about the size of human hair. But anything smaller than that gets past our nose and can actually cause damage if it reaches our respiratory system, if it reaches our lungs. Particles that are like 10 micrometers to 2.5, those can really get down into our trachea, can actually get to our lungs, and an extremely, extremely tiny, tiny, tiny micrometers, they can actually get into, and now I can't think of the name, but like the little air sacs in our lungs, areoli, alveoli, I don't remember what they're called. Anyways, anatomy wasn't my subject, but anyways, so all these matters can also cause problems, not only respiratorily, but they also can scatter sunlight. So this leads to haze. I'm sure you guys have all seen pictures of countries that deal a lot with, they have a really bad air pollution quality. And so they're like, the whole area just looks extremely hazy. I know when I was living in California, we had a whole bunch of forest fires and you would just come outside and it looks like you were in like a horror movie because there was just smoke and soot and ash everywhere. You couldn't see anything. Okay. Two different types of categories we can put these air pollutants in: primary and secondary pollutants. We're going to talk about primary first. Primary pollutants are ones that come from the source. These are direct ones that is being directly released either from a natural source or a human source, okay? These are ones that are being released into the atmosphere. So carbon monoxide released from those gas stoves, carbon dioxide from combustion reactions, fossil fuel burning, same thing with sulfur dioxide, nitrogen oxides. These are again released usually in electrical energy sources release a lot of nitrogen oxides. So these are ones that are directly being released by something. Nitrogen oxides also are released when we burn, but not, I guess intentionally or non-intentionally, when trees burn, whether it's a forest fire or campfire, because nitrogen is present in a lot of trees and their organic matter, that can also release these nitrogen oxides. But again, these are primary pollutants because they're being released directly into the atmosphere. Once these primary pollutants reach the atmosphere, all kinds of crazy chemistry happens in the atmosphere that we're going to talk about in a little bit. in those chemical reactions that are happening in the atmosphere from those primary pollutants, those reactions form what we call secondary pollutants. These have undergone some sort of reaction, some sort of transformation, and they are newly created molecules. Again, these are created in the atmosphere itself, so they're secondary. Our secondary pollutants do cause a whole heck of a lot of problems, so they're not to be like, we don't call them secondary because they're not detrimental, because sometimes they can actually end up being worse in some cases than our primary pollutants. We just call them secondary because they're not coming from the source, they're rising because of that reaction. Okay, so like sulfuric acid, we're going to talk about later when we get to acid rain. Sulfuric acid is what we would consider a secondary pollutant that came from the primary pollutant, sulfur dioxide. I'm sorry if I'm talking really fast. I just don't want this video to be super long. All right, so we got natural and anthropogenic or human-generated sources of air pollution. Some natural sources, again, we talked about volcanoes. If you think back to that sulfur cycle, this is a huge release of sulfur dioxide. Lightning, forest fires, any sort of ignition combustion, these are going to be releasing a lot of nitrogen oxides. Yeah, I feel like I'm saying that wrong, but yeah, nitrogen oxides. Plants, you're like, what? Well, plants release carbon dioxide, they take in carbon dioxide, but through the process of respiration, because remember, our plants go through both photosynthesis and respiration. Our plants are going to be releasing carbon dioxide when they go through those respiration reactions. But also, I think I talked about this maybe earlier. I feel like I've practiced this way too many times. But plants also release those VOCs, those volatile organic compounds. Remember, anytime you think of something being very sweet smelling or smelly, that is going to be a volatile organic compound, those airborne organic molecules that usually have a scent, and they're airborne because they have that low boiling point. So conifer trees, I mean, everyone loves when you go like through Christmas tree shopping, it smells really good. Well, that smell is actually a VOC, volatile organic compound. Same thing, citrus trees, all those really sweet smells are called, I always say, I feel like I'm saying this word wrong, but they're called terpenes. And those are sweet smells that are being released into the atmosphere. Y'all hopefully are familiar with these, are anthropogenic or human generated. Y'all know fossil fuel burning, especially from gasoline, releases a lot of air pollutants, power plants, any sort of reactions, especially combustion, electrical reactions. These are all releasing those sulfur dioxides, nitrogen oxides. One thing about on-road vehicles, and we'll talk about it more when we get to catalytic converters in just a little bit, in cars and gasoline. Lead air pollution used to be way higher because we used to have a high percentage of lead in our gasoline that we would use for our cars. And so as we burned the gasoline to power our cars, it would release a lot of lead. Not great. We don't want to be breathing in lead. It is a heavy metal. Rock on, sorry. But we've been decreasing the amount and eliminating the amount of lead that is present in our gasoline. And we're going to talk about why exactly that has been happening and how it's so awesome how that's been happening. I think that's coming up pretty soon. All right, so once we get all of these pollutants into our atmosphere, a couple different chemistry things are going to happen. I'm going to go a little bit fast on this because I want to honor y'all's time, but rest assured that we are going to go over this quite a bit in class. So nitrogen dioxide can lead to smog, particularly what we call Los Angeles brown smog. So usually we have what's called kind of a recycling reaction. So nitrogen dioxide makes it to our atmosphere through the power of sunlight. It gets broken down into nitrogen oxide, NO, and just a single oxygen atom. That oxygen atom combined with oxygen gas, O2, to form this ozone, O3. Cool. We would think, yay, we like ozone. Ozone we want to protect. We'll talk a little bit later about how we want to protect our stratospheric ozone, which is our like above human breathing area. Tropospheric, or down here, ozone is not so great for us because it can actually be a little toxic to us. But anyways, thank goodness there's a natural breaking down of ozone that occurs in the troposphere down here, where that O3 is going to react with those free-flowing NO, nitrogen oxides, and it's actually going to donate one of those oxygens so that oxygen gas is released and NO2 is there and the cycle continues. So when we have nitrogen oxides available, it actually helps control and regulate the ozone formation down here where those levels would be toxic. Unfortunately, when we've got those VOCs, remember VOCs are kind of like airborne, low boiling point, very smelly stuff. So formaldehyde, coniferous fir trees, anything that's got a nice pungent smell to it. In the presence of VOCs, VOCs actually bind with those nitrogen oxides. And instead of being able to break down ozone, they almost get like blocked or inhibited or occupied by these VOCs. And so those nitrogen oxides are not able to break down that ozone. And so we end up having a buildup of these pollutants. We have a buildup of ozone, we have a buildup of these oxidants, which later we're going to find out that they actually do some even more trouble. And we end up getting what we call photochemical smog. Because this is coming from nitrogen oxides, this is going to be our Los Angeles type of brown smog, kind of like what we would think of as a typical smog. Temperature also can make this even worse. So hotter the area, the more smog we're most likely going to see. Because remember, VOCs are binding with those nitrogen oxides, letting that ozone or preventing that ozone from breaking down that way. So VOCs, bad guys here, they have that low boiling point. That's why they're volatile. That's why they're in the air. So if I have higher temperatures, then I'm going to have more and more VOCs released into the atmosphere. Additionally, nitrogen oxides are usually released, especially from electrical equipment. That's the type of reaction that releases a lot of nitrogen oxides. So air conditioners and the energy usage, the hotter it gets, the more we're going to be cranking up that AC, the more nitrogen oxides are going to be released. Additionally, just in general, you might remember from chemistry, chemical reactions tend to have higher reaction rates, the higher the temperature. So high temperatures, we're getting more and more smog, pollution, and it ends up being a positive feedback loop. One more thing about temperature. Temperature, especially when we're dealing with pollution, there's a topic that it's called thermal inversions. A thermal inversion is essentially a pocket of cool air that's trapped by warm air, and that ends up actually trapping pollution. Not great. So essentially, during the day, the sun is shining, yay, and we've got what we think about as a normal temperature gradient. So very, very close to the ground, we've got high temperatures where that sun is hitting the ground, warming it up. As we get higher up into the atmosphere, you guys know, the higher we are in altitude, the colder those temperatures are. That makes sense. However, sometimes when there's a lot of pollution, we end up getting almost like a pollution cloud that's formed. As the sun goes down, the temperatures fall, it's going to cool down that air, and it's going to end up causing it to sink as it cools down and ends up kind of creating a pocket of pollution. It traps the emissions, it traps like in this little cloud where we end up having this really warm pollution cloud that is being trapped by the cold air on either side of it. So we have this weird temperature graph where we're increasing in temperature as we're going up, but then as we go out of the atmosphere, we have, that even colder temperature. But again, this is being created by that smog, by that pollution. All right, we've got a joke, I swear, right after this. Okay, acid rain, acid deposition. We are, God willing, going to be doing an acid rain lab in our class if we've got time for it. So all rain already is going to be slightly acidic. We talked about this a little bit with the eco columns, but carbon dioxide is, whenever it's in the presence of water, carbon dioxide can form carbonic acid in the presence of water. So that's going to already lower the pH. Rain itself is usually at about a 5.6 pH, which is lower than I would have thought it was. However, pollutions can actually make that an even lower pH, even more acidic. And that's where we get to see some problems. So we have our primary pollutants. Remember, those are ones that are being immediately, directly released from factories, released from different sources. So sulfur dioxide and our nitrogen oxides are going to be released from combustion reactions. In the atmosphere, they're going to combine with oxidants, which are oxidizing agents. So think back to chemistry. They're accepting those electrons. Oil, rig. Oil is oxidating is Liz. Anyways, I don't know chemistry. So anyways, we end up forming sulfuric acid and nitric acid, and we'll go over the chemistry about this in class. Don't worry. but those can then further break down in the atmosphere to form sulfates and nitrates. Sulfate and nitrate, since they've given up those hydrogen, we now have free-flowing hydrogen ions. pH literally stands for parts hydrogen. So the greater amount of free-flowing hydrogen positive ions we have, the more acidic an area is. So now we have a greater acidity that's occurring in these clouds, in these rainstorms. So when we actually have that precipitation, we end up having that really low pH, that high acidity. Again, we're going to go over this more, but I think key points here: primary pollutants, secondary pollutants, because they occur in the atmosphere. These reactions lead to acid rain. Oh gosh, sorry, I thought I had one more. Okay, when we have acid rain, you guys know this, we're going to end up lowering pHs of water streams and lakes. Not great for our salamanders and our fish friends. And as you guys learned in Wolves of Yellowstone, if we're knocking out and we're creating an unhabitable environment for one species, and that species interacts with a whole bunch of other species, we could end up having long-lasting, far-reaching impacts to all the different species that are interacting and directly affected by that species. So not great for that. In addition, you guys have probably seen those tombstones that have all the weathering happening, weathered on statues. It can damage a lot of things and release heavy metals that might be found in our soil. There's our joke. Yay, yay, yay. Not the best quality joke, but I think it's so cute. When you open the spaghetti sauce jar on the first try, it's like, okay. All right. So you're probably thinking like, holy cow, Ms. Broussard, like these are not great things. I get it. So there are a couple ways to prevent air pollution. We can do different bed combustions. This uses less fuel, so it's actually a really great one. And we're going to talk about this later on in class. Catalytic converters on cars. This is where I was like, I can't wait to tell them about this. So I think it was Kami in first period was talking about catalytic converters, something, I don't know. Anyway, so catalytic converters are now required for every single car. And it's so great that these are required is because not only do they decrease the amount of nitrogen oxide and allow the amount, oh, that's my mom, I'll call her right back. The carbon monoxide that is released in an area, but also they cannot work with lead gasoline. So if there's lead in the gasoline, it actually damages that like precious metals in the catalytic converters. So they were like, oh man, whoever came up with this was so smart, because they're like, we're going to require catalytic converters. Not only do they reduce air pollutant exposure, but also gasoline companies can no longer put lead in gasoline. So we're reducing all these different pollutants that way. But these last two we're going to actually take a look at because they're pretty neat. Yeah, these really, really quick. I mean, I think they're pretty self-explanatory. Your book does a really good job of checking these out. But essentially, with the bag house filter, air is coming through. It's being trapped by the bags. I love this one. This is our electrostatic precipitator. Air goes through. It passes through a negative electrode, gives the particulate matters a negative ion charge, which then when they go against the positive electrodes, the negative ions binds to the positive electrodes. Y'all, people are just so smart. And then the scrubber, this is my all-time favorite. It reminds me of like a car wash, but for air. So the air comes in and there's literally like water that gets like sprayed on the air. The water binds to the particulate matter in the air, clumps it, brings it down, and then clean air passes through. So it's like a car wash for air. Awesome, awesome, awesome. Oh gosh, I got a joke. My friend said this to me yesterday. It was so funny. So my Punny Monday friend, I was going to cook alligator for dinner, but I realized I only had a crock pot. Okay, sorry. I want to honor y'all's time. Second to last thing that we're going to talk about in this unit, and then I swear I'm going to wrap this up. Stratospheric ozone. So we've talked a little bit about how, especially in the presence of those VOCs, we can form ozone, which is not great for us here down in the troposphere where the little human beings are living. Not good. We want ozone to form in the stratosphere. We like our stratospheric ozone because the stratospheric ozone is what protects us from those UV ultraviolet rays. Yay, ozone. So this is way, way, way above us. It absorbs the UV radiation. I think it's like the only thing or one of the only things that absorbs UVB, which is, I'll talk about that in a little bit, but it's like middle tier UV radiation. It actually does like subcutaneous, reaches our subcutaneous layers of skin. So yay, ozone. Okay, so really, really cool thing that's going on. We should ideally have a steady amount of ozone in our atmosphere, way up in the stratosphere, because we have these awesome reactions that make the ozone and also break the ozone. So we're constantly making and breaking the ozone, which means we have a balanced amount of ozone presence. Not too much, not too little. Ideally, we're going to talk about how this ain't happening as much anymore, but we'll get to that in a second. So ideally, UV radiation is actually going to be the one that helps us out. So UV radiation C, this is the highest energy UV. So we have UV A, B, and C. UVC's got like, woo, 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 super energetic. All right. So its high energy actually takes the oxygen gas molecules in the stratosphere, breaks it apart. So I end up getting 2 free single, ready to mingle oxygen atoms. Those can then bind with a paired up oxygen gas, and that can form our O3 ozone. Awesome. To make sure that we don't get too much ozone and that it's not like end up being a problem, ozone is then recycled and broken down by UVC and UVB. UVB is one that actually is a leading cause of skin cancer. So it's good that we have the ozone to protect us from it. Yay, ozone, once again. But our O3, our ozone is going to bind with either UVB or UVC. And because, again, it's that high energy can make and break bonds really easily. So they're actually going to break it down back into the O2 and that free-flowing oxygen, and the cycle continues again. However, there is some problems that are causing us to actually lose more ozone than we're able to create it. And that's how you might have heard of an ozone hole, or a hole in the ozone layer, which is not great, because again, if we've got holes in the ozone, if it's like Swiss cheese, that harmful UV rays are going to be able to get to us much easier, which can lead to things like skin cancer and different diseases such as that. So chlorine is actually something that really puts a wrench in the system. Who would have thought? Whenever you think of chlorine, you might think of swimming pools, but it also destroys the ozone layer. Okay, so chlorofluorocarbons, which is really fun to say 5 times fast, I dare you, is used primarily as like a coolant. So it's used for air conditioning, car coolants, it's used in refrigeration, it even does aerosol cans, all kinds of things. So we use it a lot, but unfortunately, this is a man-made thing, chlorofluorocarbon. I think there's probably, anyways, chlorofluorocarbons end up getting released through a lot of different processes. And it's an extremely, what I would say, a hardy molecule. It's very stable. It does not like to react with a lot of things. And it doesn't like to be broken down. So it ends up being released into the troposphere where we are, but it just kind of bounces around because nothing can really degrade it and nothing really breaks it down. And eventually it finds its way up to the stratosphere where our good friend ozone layer is. Once it gets there, ultraviolet radiation, which is very intense up there, the ultraviolet radiation actually takes the chlorofluorocarbons and breaks it down. Now we have the free floating chlorines that can cause some damage, okay? So again, lots of chemistry here. We're gonna, I told you, a whole day is gonna be dedicated to this chemistry next week. So UV radiation took the chlorofluorocarbon, released that chlorine atom. Now this chlorine atom actually binds with the ozone molecules, those O3 molecules, to create ClO, chloromonoxide, and oxygen gas. So already we're starting to break apart those O3 molecules. And then here's the kicker. This I feel like I'm not saying this right, chloromonoxide, anyways, ClO then binds with those free floating oxygens and becomes just plain old chlorine. This chlorine then goes back to that first reaction and keeps breaking apart the ozone. It keeps just recycling and recycling because we have this reaction that frees up that chlorine once again. We can keep on destroying that ozone, those ozone molecules, because of this reaction right here and these chlorofluorocarbons. Not great. I feel like this whole class is just like all depressing stuff, but we do our best. Last 2 slides and then we are done. we are going to be doing an indoor air pollution lab because this is a really important topic, because especially in America, we spend about 80 to 90% of our day inside. Kind of sad. And there's a lot of different things, a lot of different indoor air pollutants that can get to us, even if we're protected from the outdoor air pollutants, such as that sulfur dioxide and smog. There's still a lot of stuff in here that we can get to. You probably have heard those commercials for asbestos, like, were you alive in the 60s, whatever, and you worked at this building, it had asbestos. So that one I would think it was kind of like, and anyways, probably one you've heard of. But even like VOCs and home products. So again, anything that's like kind of smelly, that is like being produced or projected into the air. So sometimes I think of like aerosol cans. So like hairspray, you know, we have now put some particles in the air that we can inhale, and that can damage our lungs. Different types of paints, like there used to be lead-based paint. So as those start to peel off, that releases the lead particles into the atmosphere. Carbon monoxide, thank goodness for that little scent that they put in there. So all kinds of different things can damage us. I'm not going to spend a whole lot of time on this because we are going to do a lab that's going to really get into this later. Oh, we're almost there. Again, 80 to 90% of our time is spent indoors. I'm going to pause the video real quick right here so you guys can answer a quick question. But a lot of different things that's going on in our area is producing these indoor air pollutants. And because we spend so much time trapped in these little bubbles, insulated bubbles with maybe not a lot of exposure and filtration, we can end up getting some damage from that. You made it to the end. Oh my gosh, I feel like this was like a 15-hour-long video. I appreciate you guys hanging in there. We do have a riddle for today. I shave every day, but my beard stays the same. How is this possible? Anyways, really great to have you guys all here, and care for each and every one of you, and I hope you have a great rest of your day. Bye.